Hi there and welcome to this first video for senior physics on electromagnetism and electricity. In this video we're going to be looking at the idea of magnetic fields. Now basically magnetic fields generate forces and these forces can affect moving charge, and if it's affecting moving charge it can generate a force which produces a push. The push on a charge basically we term electricity. As well as producing a push against charge, what we can also get is a push on an armature which is present inside a motor, and as a result we can convert magnetic interaction of magnetic fields together to produce kinetic energy, which is really useful in something like a DC motor. Now what we need to do is to know something about the magnetic field so that when we interact two magnetic fields together in the form of an electromagnet, the result is we can see whether the fields actually interact to increase the force or interact to decrease the force, and as a result we can then look at this imbalance and see what's happening. Now on the left hand side we've got a simple bar magnet, and you can see the bar magnet is basically made out of just a normal piece of iron, and what happens is the electrons are all aligned so that they generate a magnetic field. Now the key thing to understand about electricity and magnetic fields is they work at 90 degrees to each other. So if electricity is working on one plane, then magnetism is working at 90 degrees to that motion of the charge. Now, in our bar magnet, what we notice is that the field lines run from north to south. Now, we show this obviously with a line, and then we've obviously got an arrow. Now, the pictures below, coming from our textbook Walding, basically show the presence of these field lines using iron filings. What we've done is basically taken a bar magnet, put a piece of paper over that bar magnet and sprinkle some iron filings. The result is the iron will align with the magnetic field lines and they will congregate where the field lines are the strongest. The second picture to the right hand side shows that same sort of pattern which is produced from a horseshoe magnet. Now, magnetic fields are really important on the planet Earth as well. And here you can see a picture of the magnetic field which is generated around the Earth. Now, an interesting thing about the field lines on the Earth is that over hundreds of thousands of years, the poles actually change direction. And this is actually noticed if you look at magnetic imaging of the sea floor in the Atlantic Ocean. If you know anything about the Atlantic Ocean, there's a mid-Atlantic ridge which runs down the center, and it's continually widening. Now, every few 100,000 years or so, the poles change, and the iron which is present inside the crust causes the electrons to move in one direction or then move into the other. And what you get is a banding pattern which forms across the actual Atlantic Ocean when looked under certain imaging. Now, the point of having a magnetic field around the planet Earth is to protect us from cosmic rays, and you can see the right-hand diagram is there to basically illustrate what's happening. Now what we're going to do now is look at one of the PhET simulations to just talk a little bit more about electric fields and how they interact. So what I've done is also put the link up on this post, which will allow you to go and actually have a play with this simulation. So let's see what happens when we load up that simulation. Okay, so we'll load it up now. Okay, so now if we have a look at this, the picture that we've got here, I'll just open it up so you can see in a lot more detail. Okay, so down the side here we can see what's happening with respect to inside the magnet. And we notice that basically we've got a field line which is running all the way down. Now we can move our magnet around, okay, and you can see the arrows which are moving outside of the bar magnet and producing our pattern. Now I want to start off by just showing the planet Earth. So there's the planet Earth, and what's happening here is it's radiating from north to south. Now if I use my compass, we can see that as I move my compass closer to the north or closer to the south, you can see how the needle changes. Okay, so as a result, we get our nice pattern of our field lines which are generated around the planet Earth. Now, another thing that I can do is actually put a meter in. Now, where this cross basically sits, this meter will actually measure the magnetic field strength. Now, what I want to do is actually look at the magnetic field strength here. Okay, don't worry about the units. It's the concept here which I'm interested in. So here it's reading 0.12, which is just outside, almost outside of the Earth's atmosphere and well away from the planet. It's almost getting down to zero. But look what happens when I start moving it in. As we start moving closer to the planet Earth, we see that the strength of the magnetic field actually increases. Now, what we'll also notice is that the field lines are getting closer together. By increasing the number of field lines, the result is we're going to get an increase in magnetic field strength. Okay, and you can see it getting gradually bigger. If we take the same thing and move it up to the top, we can see it doesn't matter where I place it. In fact, if I try and place it in the same distance around the planet, the idea is that we're going to try and get a similar sort of process. So we can see that the magnetic field, basically the closer we get to the planet Earth, the stronger the strength of that magnetic field is going to be. Okay, so let's go back and have a look at the bar magnet. And in this case, what I'm going to do is again use my compass. My compass here, this is going to be the north, and this is obviously going to be the south. As I move my compass around, you can see that the compass needle will change depending on whether I'm going towards the north or whether I'm going to go from the south. So the red line denotes the arrow. That's the direction that we're going to be going. So as I move my compass, we can see that the field line is running from north to south. Put my field meter in, I get exactly the same. The closer I get to each of the poles, the stronger it becomes. Okay, so the strongest is right at the tip of the pole, and then the further away I get, the less the field strength is going to be. Again, if I take this right out here, right up to the corners, you can see that it's pretty weak. Okay, take it into the center here, and it's getting gradually stronger. It's not as strong as we would find right at the poles though, okay, because you can see right at the poles, I'm going to have huge numbers of field lines coming in. We call that magnetic flux, and we'll discuss that in the next post. Okay, so basically what we've now discussed is we've looked at the different types of, we've looked at the bar magnet, we've looked at its effect around the Earth. We know that as we get further away from the bar magnet, the field strength decreases. We can change the polarity using this program, and all that does is change the direction. You see the needle changing. We'll change it again, see the needle moves again, change it one more time, you can see that needle moving. We can also change the field strength. By changing the field strength at the top here, you can see how my magnetic field from my meter starts going down. And we're decreasing until there's nothing left. Okay, so now it's not a magnet. Okay, and if I wanted to look inside the magnet, it's not going to show anything there, but basically we would see that the electrons are not aligned. Okay, well I hope you found that useful. Do go on to this PhET program and have a play, and we will then be utilising some of this information later on when we start introducing more of magnetic field interaction. Okay, thanks for watching, and join me again.